Hello everyone, I'm Zahid Hassan Tushar. I'm a first year PhD student at the Department of IS, UMBC, and I welcome you all to my presentation on automatic speech recognition in federated learning framework under adversarial attacks. Motivation. Automatic speech recognition ASR is an automated system which recognizes human speech for various human computer applications such as telemedicine, patient care, voice assistant. Now, some example of voice assistant could be Alexa and voice Google Assistant. Now, most of these ASR systems are centrally trained, which makes them vulnerable to adversarial attacks and leakage of user information. How does it happen? So the company is collecting data from all its users, and then they are training their model using those data in the server. Now, if the company has bad intention, they can misuse the data and thereby violating users' privacy. Now, recently there is a new learning paradigm in AI, which is called federated learning. In federated learning, the data do not leave user device. Therefore, during the training, therefore it is more secure than centralized training. In federated learning, training is carried out on edge devices such as mobile phones, other smart devices by sharing a global model and without sharing the device data. So it is also beneficial for the company at the server side as well because it requires less storage and computational power for them. As I was saying that in federated learning, there is a global model at the server and they share this model to the clients or the devices. And at the device size, they use the local data to train this model and they send back only the updates to the global, to the server for aggregation. Now, it might happen that one of the client is an adversary and they did data poisoning to their data and they use this data to train their model and then they send this corrupted update poisonous update to the cloud for aggregation which will in turn poison the global model and the performance of the model will degrade. This is one kind of adversarial attacks. Now, most of the federated learning frameworks are designed for NLP and computer vision application. One or two federated learning implementation for ASR are found, but they are not extendable and they do not have all the functionalities of federated learning. Also, a few federated learning algorithms are proposed for ASR, and not all of them are practical. We have found one practical algorithm called FedNST, but there is no publicly available implementation. Also, there is no federated dataset for ASR, which is publicly available. Objectives. Therefore, we are proposing to train ASR model in federated learning. So for this, we are proposing to extend the FedML, which is a federated learning framework, to include a new federated speech dataset, an ASR model, and the FedNST algorithm. After that, we will evaluate the performance of the model under different adversarial attacks such as data poisoning and inference-time attack. Proposed methodology. How does FedNST work? FedNST is a semi-supervised learning algorithm. So there is labeled data and there is unlabeled data. So for this setup, we are considering the server has the labeled data and the client has the unlabeled data. So using the labeled data, the training happens at the server. After the training, the global model is achieved. Now this global model is transmitted to the clients for client training. Now the client trains this model using the client data and then they send back the updates to the server. The server accumulates all the updates to compute the client update. At the same time, the global model is also being trained at the server using the server data to compute a global model update. Then those two updates are combined together to ultimately get a global model. Now this process is repeated until convergence. Now, there are three components to our experimental setting: dataset, model, and loss objectives. I will go through them one by one. Dataset. For the dataset, we are using LibreSpeech data. LibreSpeech corpus consists of English audiobooks containing 1,000 hours of speech sampled at 16 kilohertz. Out of them, 960 hours belongs to training set, and the rest belong to development and test set. The audio files have extension, and the labels have .txt extension. The size of the dataset is around 60 GB. Federated dataset. Important property of federated dataset is the non-IIDness. In practical scenario, all the users will have different data distributions because everyone speaks differently, and also the size of the data won't be the same. Some may have speech for 5 minutes, other might have speech for 30 minutes. It can be understood from a computer vision application. For instance, all of us have mobile phones, and someone might take 100 pictures a day, someone might take two, someone might not take any pictures. So the data, each client will have different size of the data. And now the federated dataset has to reflect this non-IIDness. How do we achieve this? We consider each speaker in the lived speech dataset as an individual client. Since our algorithm involves a semi-supervised setting, how do we achieve that? First, we sort the data based on the duration of the speaker, and then we select alternatively speakers for each group, one group for client, one for server. The server has the label data and the client has the unlabeled data. We don't use the label for the client, so that's why it's just unlabeled. So in this way, we got 1170 speakers for the server and 1160 speakers for the client. Now, the 1170 speakers for the server is not used separately because it's one part of data, but for the client side, each client will have data based on the speaker. Data augmentation. For the data augmentation, we're using speed part up. It slightly speeds up or slows down an audio signal. In other words, it resample the audio signal at a rate that is similar to the original rate to achieve slightly slower or slightly faster signal. If this is the original sample, then a part of it is speeded up and a part of it is slowed down to match the whole length. Now, what this means practically? So it means that someone is speaking at a faster rate or someone is speaking at a slower rate, but the content of the speech sample remains the same. Model. This is the model we are using. There are multiple blocks and I'll go through them sequentially. So first, the speech data is fed to a feature extraction block where the features are extracted. We can use multiple feature extraction technique, mail spectrogram, filter banks, and then the extracted feature are fed to a CNN frontend. Now this is a three convolution layers. CNN, it has three convolution layers with leaky ReLU as the activation function, followed by a 0.1 dropout layer. Then the outputs are passed to a transformer block. Now this transformer ASR is implemented using attention is all you need paper information, and we have we have 8 layers in the encoder and 6 layers in the decoder, but with 4-head multi-head attention block. The output of the encoder is fed to a CTC, that is a connectionist temporal classification linear block, and the decoder output of the decoder is passed to a sequence linear block. Those two blocks are actually one fully connected layer. The outputs of those two block is passed to a loss objective block where the loss is computed using the outputs from them, and during the evaluation and test time we use the output of sequence linear as the prediction. Loss objectives. Loss is computed using a combination of the connectionist temporal classification and sequence to sequence loss. Now the CTC, connectionist temporal classification, it calculates the loss between a continuous time series and a target sequence. Sequence to sequence is actually computes the KL divergence loss between the predicted and the target distributions. Ongoing work. Currently, we are working on the training module, on the implementation of the training module. After that, we will move on to adversarial sample generation, for which we'll be using pulse adversarial samples. And then when the adversarial samples are generated, we'll evaluate the performance of our model under adversarial attacks. Here are the references for our work. Thank you for listening.